Continue talking about how your body is able to exchange gases with its surroundings and then also what's going on at the tissue level. So, when we talk about gas exchange, it's really due to two pieces. One, the partial pressures of the gases themselves, as well as the solubility of that particular gas. So, something that's interesting, and a lot of kids don't necessarily think about this, is that CO2 is actually way more soluble in your blood than oxygen is, which is why we've had to evolve things like the hemoglobin in your red blood cells to attract that oxygen to get it to stick, because the CO2 actually kind of naturally wants to be there much more easily than the oxygen does. We also have to talk about the respiratory pressure. So that when we talk respiratory pressure, we're talking about what's going on in your lungs as opposed to the pressure outside in the atmosphere, in your surroundings. So there's constantly pressure exerted by the air surrounding your body. When that negative respiratory pressure is less than atmospheric, that's going to allow gas to sort of get pulled into your lungs. Remember, we do negative pressure breathing, as opposed to that positive respiratory pressure, where now that gas is going to get expelled out of your lungs and back out to the atmosphere. So think of that partial pressure just like we would talk about a concentration gradient. So it's passive transport, and so those gases are going to move from where they are at a lower pressure to where they're at. Where they're at a higher pressure to where they're going to be at a lower pressure. So when we look at the transport of those gases, right, you've got blood coming to your lungs that has a low partial pressure for oxygen, a low concentration. If that makes more sense to you, then think about it that way. It's fine, at least for our purposes. So it's low partial pressure in your blood, but it's high partial pressure for the CO2. So what's going to end up happening is we're going to take a breath in. Your alveoli are going to fill with oxygen because now that pressure differential high out in your surroundings, low into your lungs, and then we take a look at this here. So now that oxygen is high up here in this alveoli, low in your blood, so it goes from high to low. The reverse is true for your carbon dioxide. So it's high pressure here, low in your alveoli, and when you exhale back out, now we're going to talk about high CO2, low CO2, and so it's going to flow back out of your body as well. When you get to your tissues, the pressures are opposite. So now that oxygenated blood is being pumped from your body to your capillary beds, so there's high oxygen in the blood, low oxygen in your tissues, because your tissues have been using it all to go through cellular respiration to make energy. But the byproduct of cellular respiration is that CO2. So now that's high in your tissues, but low in your capillaries. So the CO2 diffuses back out, goes back to your heart, gets pumped to your lungs, and the process reverses itself. So it's those changes in partial pressures that cause all sorts of things to happen. One of which is actually the change in the diameter of your bronchioles. So your airway passages, those branches that are breaking out into your lungs, are there to service areas where your alveoli carbon dioxide is highly diluted, okay, or highly dilated, I should say, to get that material out. Because remember that CO2 likes to actually be diluted and in solution in your body, so we need to get rid of it. If they contract, that's going to end up hanging onto that oxygen. So there's all sorts of factors that are important for that gas exchange. The partial pressures here again, the solubility, but as well as those two pieces, we also have to talk about your respiratory membrane structure. So we mentioned surfactants, and that's going to come back in here, as well as matching that ventilation and perfusion, that opening and constricting of those airways so that we can get material in as well. So if we look at your alveoli, right, and zoom into those little air sacs, remember that those guys are these big sort of grape-like structures, and their purpose really is to increase surface area. The more surface area we have, the more area we have for this gas exchange to happen, but the thickness of those membranes also plays a role. And so not only are there just a lot of these air sacs, but they're also really thin. And in fact, they're usually somewhere between 0.5 to 1 micrometer in thickness. And that's going to also help to facilitate efficient diffusion of these gases. Because remember, diffusion is really only efficient over short distances. In terms of looking at your actual airway itself, your air lung capacity. Most men, at least on average, have somewhere on the order of 60 meters squared of total surface area because of all these alveoli that exist. Now, if those membranes become thickened because they got waterlogged, pneumonia, for example, might be something that can cause that fluid buildup. That gas exchange becomes inadequate. Your body ends up getting deprived of oxygen, and there's all sorts of resulting side effects that come along with that. So we can look at your alveolar ventilation, or your AVR. So what this ends up looking at is how many milliliters of air are you actually able to take in per minute. So it takes into account your frequency, how many breaths are you taking. So it measures that flow of fresh gas. So we can use this for a whole bunch of diagnostic techniques. Asthma might be one. Your AVR is not adequate to a normal resting level. We also look at just, are you taking short, deep breaths, rapid, shallow breaths, and how does that end up corresponding to your ability to properly, effectively take in the amount of oxygen and get rid of the amount of CO2 that you need so that your body is efficiently doing that gas exchange to then get those gases to your tissues for cellular respiration. So there's all sorts of factors that can increase or decrease that AVR value. The depth of your breath, how thin is your respiratory membrane, how many capillaries are there, and how narrow are those capillaries. Once again, there's a surface area piece. Other things that can actually decrease your breathing rate, things that often end up happening to people because we're doing it medically or because they're doing recreational things or there's other disease processes happening. Depressants will actually cause your breathing rate to slow down, become deeper, more shallow, slower, and so that can decrease that ventilation. Anesthetics. All right, so when you go in for surgery, your anesthesiologist's job is to measure and watch this AVR, watch your breathing, make sure that you're getting enough oxygen to your tissues. Any sort of increased resistance to your bronchioles. So there's the asthma piece. All right, people who have that wheezing, it's because their bronchioles are tightening, and as a result, their body is trying to increase their breathing rate because they're not getting enough oxygen to their cells, and their cells are screaming to the brain, hey, guess what? This is a problem. It's a feedback mechanism. Tumors can also do this. Increased compliance, or reduced compliance, infections, arthritis in your intercostal muscles, scoliosis can cause this, any sort of decreased surface area, heart disease, emphysema, thickening of the membranes, so think of things like pneumonia and getting that fluid log, right, or any sort of reduced blood capacity in order to actually transport the oxygen. All of this is going to decrease the amount of oxygen that's getting from your lungs to your tissues and the CO2's coming back the other direction. So it's a big homeostatic mechanism. All right, you've got this piece in your medulla oblongata whose job it is to measure the amount of oxygen coming into your cerebral spinal fluid. And if that is not being done appropriately based on actually your blood's pH, it's going to stimulate all sorts of things to happen to get your breathing rate and your heart rate up or down if necessary in order to do this. So your medulla oblongata's job is specifically to measure the pH, and so it's going to watch and regulate the rate and the depth of your breathing in response to that. Also will adjust some of the breathing rate and the depth to match your metabolic demands. So if you're out running a marathon, obviously you need more oxygen. All right, you're in a fight or flight situation, you need more oxygen, so we're going to do that. And then your pons, which is also part of your brain structure, regulates the tempo itself. All right, so it's sort of working in conjunction there. Now you've got sensors or cells whose job it is to watch these levels as secondary control centers in your carotid arteries, which go up through your neck, as well as in your aorta. All right, so you've really got two major pieces watching to make sure that your blood pH is staying in check, because that blood pH is connected to your CO2 levels, which in turn are then connected to your oxygen levels. So you've got certain factors that are promoting that gas exchange between your systemic capillaries and your tissues, but they're essentially the same thing that's happening at your lungs. It's the partial pressure, it's the diffusion gradients. The only difference is here now the roles and the pressures are reversed. So when we look at your lungs, right, oxygen high here, low CO2 in your lung tissue, and the pressures here in your capillaries are reversed. So high CO2, low oxygen. We get to your tissues. Now I've got higher CO2 than I do in my capillaries, but my blood has a higher oxygen, which is what you're seeing here, to facilitate that diffusion in the opposite direction. Now, in order to make this work, right, we said that CO2 has a much higher solubility than the oxygen does, which means in order to ensure that that oxygen actually gets taken up efficiently and gets moved around your body effectively, there are certain proteins that are there to carry that oxygen to increase that amount that the blood would naturally be able to carry as just a typical solution. And there are different options. So if we look at things like arthropods and a lot of mollusks, they actually have this compound called hemocyan. Their blood is actually like a bluish color by nature, and it's because they're utilizing that molecule with copper as their oxygen binding compound. In us, as well as a lot of invertebrates, we use the hemoglobin, and it's in connection with that iron, which is what gives our blood that red or rusty color. So if we zoom in and look at bonding to the hemoglobin itself, all right, each hemoglobin molecule is actually capable of hanging on to 4 molecules at a time. And the binding of that oxygen to that hemoglobin and then the unbinding has to be a rapid but reversible process. So when you look at how this works, those tissues need to be able to get that oxygen as they need it, which means the hemoglobin needs to unload it quickly, especially in a situation where we've got some sort of high metabolic demand. And when we get to your lung tissues, we've got to be able to do the opposite. So if you look, hemoglobin that's released the oxygen is considered reduced hemoglobin. So that's what this is referring to. When it's in combination with oxygen, they'll write it this way. And so you get these dissociation curves that show those small changes in partial pressure that result in these big changes of oxygen delivery. So when we go here at your lungs, you're coming in with that reduced hemoglobin. We need to load the oxygen. We get to the tissues. Now I've got that oxygen bound to that hemoglobin, and now I have to reverse the process. So what we're looking at here are these things called Bohr shifts. Your CO2 production during cellular respiration actually reduces the blood pH. In order for that CO2 to get transported, it's a gas. You can't have gases bubbling in your blood. That's not a good thing. And so in order to transport it, your body turns it into carbonic acid. And so the more CO2 your body is producing because of that CO2, or excuse me, that cellular respiration process, the lower your blood drops. So that decrease in blood pH, all right, actually decreases affinity for hemoglobin for the oxygen. That's that Bohr shift idea. So the more CO2 that I make, the lower my blood pH becomes, and so the binding of that oxygen to that hemoglobin is now becoming more and more unstable, because hemoglobin's a protein, so we're shifting its structure because the pH is changing. We're sort of denaturing the protein without completely allowing it to fall apart. So at the tissues then, we have to be able to allow that oxygen to get unloaded. But I also have to maintain a reasonable pH level without getting too low. And so your tissues, you'll actually produce this bicarb, which quickly diffuses from your red blood cells into the plasma, causes this thing called a chlorine shift to counterbalance that negative bicarb ions that are there. All of this is meant to keep your blood within a reasonable range, so that we can allow that oxygen to get unloaded without totally destroying all sorts of other proteins that are hanging out in your blood. And so that's what this is looking at. So here's your tissue cells. All right, all that CO2 that's getting produced by your cells, because they're going through cellular respiration, that CO2 is going to dissolve into your blood plasma across those capillary membranes, because I've got high CO2 here, low here. And what you're doing is, here's where we're turning that into that carbonic acid. Okay, so that carbonic acid then is going to take over and cause this chlorine shift to happen. And what that does is, as that blood pH is lowering, chlorine is coming in here, and that's going to pop off that oxygen from that bound hemoglobin. Once the oxygen is released, that oxygen then can diffuse across the capillary membrane into your cell tissues, and now it's available for cellular respiration to happen. We get to your lungs, now the whole process has to reverse. So those bicarbonate ions that we were producing to maintain at least some level of pH, they get moved, instead of out of the red blood cells, now they move in. And that's where that carbonic acid comes from. That carbonic acid has to get split, though, in order to release the CO2. So we actually have a carbonic anhydrase that hangs out in the capillaries near your lungs. So it takes the carbonic acid, turns it back into carbon dioxide and water. The water stays in the plasma. The carbon dioxide now diffuses across into the lung tissue, and you breathe it out. And so that's what's happening here. So here's that reduction, that re-release of that CO2 and water. So carbonic anhydrase is here helping that process happen in your red blood cells. It's also happening naturally in your tissue fluids because of the reverse chlorine shift that's happening here. That's going to unload that CO2 into your alveoli because it's high here, low here. You just took a breath in, so high oxygen over here. Because we've allowed some of these things to move around, now I'm able to take that reduced hemoglobin, add the oxygen to it,